if you want, yes, I have remote labs. So, what was this? Problem is that something crashed and then all my windows got shuffled around. Okay, we can start with something general. So, who of you has ever used FPGAs or something?
Most of the
but only in the undergrad course, yes? In the beginning, but not for computing or anything else, yeah? It was just, you type a little, this processor you wrote, yeah?
Yeah.
Okay, so, I can show you a few things, maybe. So what you see on the screen, I have the same thing with the board actually running in Norway at the moment, where I was before. This is where I get these cool sweaters. This is why I went there. So, as you guess, the best sweaters all over the world in Norway. Norway is expensive, by the way, so take a lot of pounds with you if you want to get one. Okay, so I have this set up, and if I search a little bit, I will find this. This is, I can give you the login credentials where you can actually upload and your own project. So the way, what I have in mind to do with you, if this starts. Hello, Houston. Okay, looks lovely. So this is a tiny module, and no, don't touch. This is VHDL. If you want to go for Verilog, it's the same thing. It's very simple. So what the whole thing does is, you know how a VGA signal looks like? How it works on a screen? It's very simple. You have one signal that says, I have a new frame that starts, and you have one signal that tells you I have a new row that starts. Yeah? So whenever you have written a frame, you say, okay, go to the beginning of the frame, and then you write row by row, from left to right, top down. Yeah, one row, as you would write with your hand. Okay, and each clock cycle, you get a new pixel, and then it's like a bitmap if you want so. Bitmaps are actually stored upside down. The bitmap is stored bottom up, but minor detail. So here you get data in top down, okay, and you have RGB values that are stored. So you get a 32-bit vector, and this 32-bit vector, the least 24 bits are your RGB color values. And if you want, you can implement this algorithm I showed you before. It's actually on this. On the project website for this course today. I uploaded this yesterday, a small description. If I get somehow used to my 1,000 windows, I might figure out where I have it. But it's on the workshop website. Okay, and it doesn't matter if you take Verilog or VHDL. If you're familiar with Verilog, no problem. Just consider you get a 32-bit vector in, pass everything through, okay, except the least 24 bits are RGB values. Yeah, so if you detect, for example, color and you want to change the color, you simply override this 24 bits with something you can do on your own. Okay. Except this undergraduate course where you do a processor, you haven't done FPGA design, I guess, yeah? Maybe I have one nice example. This is what I just did recently for fun. I should. So this is, that's the programming tool. I just browsed to something. one. I'm not 200% sure. Let's give it a try. Okay, I changed the configuration. With a little bit luck, we see the output here. This is actually quite cool. So a DVI signal is pretty much the same as the digital version of this vintage analog VGA you have. Okay, this is Mandelbrot. I compute. You saw Mandelbrot before, yeah? This is not optimized at all. Okay, this is nothing specific, but Mandelbrot simply looks cool. Yeah, and I can try to find the code for this, that you get an idea how simple it really is. And I was surprised because the first test I did was working right away, which is typically a bit unusual. And this is a bit difficult to debug, as you want to see that the effect looks really cool. Yeah, with the zooming and so forth, and the colors you play around with. Do you see this there? Yeah. Yeah. In principle, I could bring it on the big screen. I'm not sure if this works. Should we give it a try? Poof. Yeah. Come on.
Try the next one.
No, not supported. It is this cable. Yes, I've put into a resolution that the monitor can't display.
Okay. Well, this is 800 by 600. This is really not supported by many screens. Doesn't matter. Okay. Well, if you get in the center of the Mandelbrot, it gets you have to process quite a long. So each pixel is now, I think it's 2,000 iterations I set it to. So each thing takes 2,000 clock cycles to process. This is why it slows down. In the worst case, I have a frame update rate of 0.5. So every other second I get an update. Okay. I can try to get the code.
So you're not into less than that?
So I use on-chip memory as a frame buffer.
Yeah.
And whenever I'm done with computing one frame, I start from the beginning, and the display you see is completely independent from the processor.
Okay.
So I read out with the pixel clock, and I have my processing. Well, the processing is actually done in the same way, as I was a little bit lazy. And let's go a little bit down. Yeah, just that you see a little bit the code. Let's go to the fancy parts. There are some things that are just for, yeah. So, who hasn't heard about Mandelbrot before? Don't be ashamed. Okay, very shortly, then we go on Wikipedia. Yes. So, Mandelbrot is really awesome. The beauty with this stuff is, it's a very simple formula, iterative formula, you compute, and you get this wonderful fancy pictures. Okay? And have you heard about complex numbers? Also, okay, no problem. You don't really need this. What you do is, you have a point here that has an x and a y coordinate if you want so, okay? And then you take the x and y coordinate and square it, and then you take the original point, add it on the result, and you iterate. And what you want to figure out is if you run away from the center to infinite, or if it's bound somewhere. That's the soft, yeah? And if you consider, you take a point that's close to the center, so it's much smaller than 1, yeah? Then if you have a small number and you square it, it gets even smaller. So if you're on the center, you are trapped here. But if you are here, you have a large number, and the large number squared gets even larger, so you escape, okay? But the cool thing is, if you are on this borders here, then it's not easy to decide. And then you try to figure out if you do this iteratively to try to figure out if it's converges or diverges. And let's say mathematically this wasn't 200% correct, but enough to understand. But the cool thing is if you are at the corner, you can zoom in to any extent. To any extent means hundreds, thousands of bits if you want so. And you can get these fancy patterns. And to compute this is what you see here. Further down, there's the C code. Get closer. Don't get seasick. Here we are. So what you compute is basically that's the whole loop function. What made the figure here, and it came back here. So what you do is nothing else as you square the x value, you square the y value, you add your original point for one component, you do this for x, you do this for y. So this is just the second binomial formula, no magic, okay? And what you do is, whenever you run through, you have a loop counter that counts the number of iterations, okay? And you say, you do this until you know if your sum of your vector is larger than 2. So you don't take the square root, yeah? This is why it's 2 multiplied by 2. Yeah, so if your vector has a certain length, you know it will diverge to infinite. Okay, then you are done. Or you have a maximum number of iterations, and the color value on the screen you see here is nothing else as the number of iterations. That's the whole magic beyond Mandelbrot in a nutshell. And you see the algorithm is really hello world. Okay, and if you would do this on a processor, if you compute this, you have one multiplication, another multiplication, one compare, another compare. These two multiplications you have, you can save this result, yes. Then you have one addition, you have another multiplication, this plus here, another add, and your loop iteration. And if you do this in hardware, you do the whole thing in a single clock cycle, basically. Yeah? It's not necessarily good to do things in a single clock cycle. I haven't talked about this, and this is today a little bit about programming. Programming for an FPGA is fundamentally different from what you use for a normal processor. The point is where these chips are really strong is if you have data flows. Data flows means, consider you have a production plant, like you want to produce a car. Okay, then you have this car that moves through the production plant, and at each stage you do a different thing. Yeah, some guy mounts a tire, one puts in an engine, whatever. Yeah, and here it's pretty much the same. You have data tokens that move through the chip, and you do different processing along the way. You can consider that you have a very, let's say, most ideally a long loop body, and you simply unroll it, and you go from one instruction to the next, and you simply pipeline the result further. This is called stream processing, typically, yeah? And this is the native model, what you have, for example, for network processing, if you do things like this. And if you have this problem, nothing will beat these chips. They are very strong for this one. Yeah, if you take something like a GPU, for example, they have a thread level programming model. So if you would implement Mandelbrot in a GPU, then each of your if you want to do it fast on an FPGA, you would have a dedicated multiplier for this one, a dedicated multiplier for this one. The result may be a dedicated subtractor and so forth. And you simply go from one stage to the next stage to the next stage. You have really a physical instance running on this. However, if you go to a GPU, for example, you would run this whole thing as a code, as you know from the normal software world, and you would have multiple threads running in parallel, and each thread works on different pixels. Yeah, it's a different way to do this. But this is important to understand. Both works, and for this specific problem, both would jam a lot. However, if you do this pipeline processing, you have a very tight coupling and synchronization between the processing elements. Yeah, so if you would implement it in a pipeline fashion, you know exactly that in one clock cycle you do the multiplication. In the next clock cycle you do this multiplication. In the next clock cycle you do the subtraction. You can orchestrate explicitly. And this fine-grained synchronization is something you don't get basically from any other programming thing. So if you go to a multi-core machine, doesn't matter if you take Xenon or your Core 7, or if you take a GPU, you don't have this fine-grained synchronization mechanisms. And this is the specific strong part you can do with an FPGA. So I don't want to say that this is the solution for everything. Yeah, not everybody uses it, and this programming this stuff sucks a little bit, to be honest. Yeah, so the abstraction level is rather low at the moment. It's most likely a little bit like assembly programming if you want so. But the reward is high. So if you if you go for things like MMX extension, simply extension in modern processors, a lot of them are programmed in assembly as well. So I think nobody ever used MMX by using high-level compilers, not that I know. So some of the things, if you want to exploit special features, you have to do. Oops, my battery is going. I might have to sneak out once if my battery goes dead. Yeah, but this is important that you carry this with you. So if you have the stream processing, a stream processing problem, this stuff is ideal. And the way how it works is really that you try to basically, for example, unroll a loop body, and you can consider if you do this that this behaves a little bit like a production plant, like for cars. So, yeah? While if you would do this on a GPU or a normal CPU, you would execute the whole loop body sometimes. Yeah, and it depends really on the application what is best. Yeah, there are a lot of applications where it's native to do it in this pipeline fashion. For example, I am trying to examine this for database acceleration at the moment. If you do database acceleration, you have an SQL query. Then you have, for example, in the beginning you have string compares, yeah, where you say where name is Hugo and age is 42 or something. Yeah, so you have string compares, you have an integer compare, and what you would do is you stream your data over the different filter elements. And then you have a dedicated filter for string, you have a dedicated filter for integer, floating point, you do aggregation, sorting, joins, and all these things. Yeah, and you can process this or very nicely in such a streaming fashion. Now that's a little bit different from what you do on a normal processor. And if you consider something like clock frequencies, an FPGA is rather slow as compared to your Xenon processor or something. Yeah? We are not talking about gigahertz clock rate. We are talking about maybe peak performance 500. This one won't ever do 500 megahertz. Yeah? We have FPGAs that might get up to 500, but this means a lot of tweaking. Realistic is maybe 300 megahertz, which sounds boring slow. But the point is, consider that this thing is very long. Yeah, you can put in with the 300 megahertz a new data item inside your processing pipeline. Yeah, so the fill rate is still quite high. So if you consider you have 100 instructions you have to process inside such a loop body, yeah, and you can run at gigahertz rate, this sounds nicely, okay. But if you are just an order of magnitude slower, but you can put in a data token each clock cycle, you are still 10 times faster. Yeah, so clock speed is not necessarily the answer for high performance. But of course, this expresses that you have problems, or where you have a large problem, like image processing, where you have all the pixels coming in and you do basically the same thing. For a single pixel, you won't do this way. Then a programmable solution on a CPU would be better. Yeah, okay. So, after so many minutes, we all know Mandelbrot, and we will dream tonight about this algorithm. And and we can have it in red as well. Come on. Yeah, yeah. I have a cable upstairs. Okay. Don't touch. Don't breathe. Okay, and this is exactly the same algorithm done on an FPGA. Yeah, so what have I done? 2 thick fingers. I just go down. So, what I do is, I take, this is x multiplied by x. Okay, this is x squared. This is y squared. Then for this comparison, if it's larger than 4, I can add. And you see, you can use normal operators you use in every other language. There are typically some things a little bit tricky if you go for FPGAs. And this is the number representation. So here I compute with fixed common numbers. Yeah, so I don't use floating point. On a normal CPU, GPU, or whatever, you would use a floating point representation. Floating point is not necessarily good. Why? So if we go to Wikipedia, one of the best inventions of mankind, it's so cool. My favorite article on Wikipedia is about fireflies. Hold on, where was this one? This one. So the problem you investigate here is scaled. So in the center is 0. This is -1, -1, 1, 1. Now, so it's in the range. The number range is just something like from 0 to 2. Okay, so you don't have a problem that scales to millions, billions, trillions, or whatever. So in other words, if you look on a floating point representation of your numbers, you won't play around with the exponent. The exponent would always be something like 0, 1 or something, yeah? But you don't shift the commas to very large numbers. You don't compute with very small numbers, because in the center there is nothing spectacular, and you don't compute with very big numbers. So you don't play around actually with your exponent. So if you have this situation, if you have the situation, I shouldn't dance too much here. If you have the situation, then playing a floating point is not good, because you're only interested in the number of mantissa bits you have in your number representation. So if you say you have a, let's say, 32-bit number or a 64-bit number, let's say you take a double precision number, that's a 64-bit, there you have 54 bits mantissa and the rest is exponent, then the exponent bits are basically wasted, and you would actually prefer to have more mantissa bits. But, well, your processor doesn't allow you to do this. Well, if you build your own dedicated hardware accelerator, you can do exactly this. And as you see, you get this even in red. I need something heavy. Yes, and so the number representation I chose was simply 2 digits before the decimal point and the rest afterwards. And if you square this, well, then you get 2 digits. Yeah. So whatever you do, you have to keep track about where your comma is. Yeah. That's the only tricky part. And this is why I was surprised that it working right away when I implemented this. Yeah. And so then I can compute the sum and so forth. This is this pixel done. This was exactly this comparison. If I say I have this maximum count thing, or if I have the sum, if it's larger than 4, I don't use 4. I just know 4 is this binary representation. So I just ask for the bit. So this is a little bit geeky programming. You not necessarily have to do this. Okay. And I think a little bit more in bit vectors. Yeah, and this is simply exactly the other formula you saw. This looks a bit strange here, so that's the square number, and here I'd simply take the most significant bit of the number and I add it a few times. This is just, I have to extend the number with a sign bit. Yeah, I compute with sign bits, and if you extend the vector on the front side, so all the things you learned in your first semester come back if you want to do this on a machine. So you have to be aware, you don't get this for free. So that's a little bit the tricky part if you do this. But if you have done this, and this is really the whole loop kernel, just these few lines. The rest around is, what I programmed is only that it looks somehow fancy on the screen, okay, and doing the video I/O. But this is the whole loop kernel that represents the same thing you saw on this Wikipedia thing before. Yeah, just that I don't, so this looks definitely a little bit different as you have to think about the bits and so forth. But the thing is that the whole loop kernel here, I compute in a single clock cycle. Typically, you wouldn't do it in this way. So if you want to do it really fast, you make this over multiple clock cycles, but you get a higher clock rate, and you compute a new pixel in each clock cycle. Yeah, and If I will have definitely one lecture on Mandelbrot once later, where I will go a little bit more into detail. But this is just to give an idea what you could do if you use an FPGA. What's the problem? Okay. And this is what happens if you have an overflow somewhere. I don't know what really happens. So at one point it does some fancy things. I haven't put in something to reset it. So if I want to do this, I have to reprogram it. Okay, so the setup I use for Mandelbrot, by the way, is exactly the same one that I use for the skin color detection. And I think if I search a little bit, I will actually find one module where I did the skin color detection. So this board actually has DVI input and output, and don't move. Has DVI input and output. Quite interesting. This is a clock rate that's each I/O pin on this chip provides or can be run at a gigabit, which is quite a lot. Each individual I/O pin, and I have far more than 100 I/O pins. So the I/O speed you can get on this single chip is quite a little bit. And this is one of the rather smaller devices we have. Okay, and so basically the cable, the DVI cable, goes directly to an I/O pin of the FPGA. There is not really something in between. There is one driver chip in between, but in principle even this wouldn't be necessary. And you can go with this high data rate, which is quite impressive from an electrical point of view. Okay, so if you're interested in making your hands dirty, writing some hardware, you can go on the, we can take this one, hold on. Let's see, put a link. No, okay, hold on. Ultimate Programming, Manchester. Google is the answer on everything. Hello. Today, please. Where is it? No.
What are you looking for?
We have one on Google somewhere hosted.
The App Store. You're after the workshop page.
Sorry? Yes?
It's sites.google.com. It's not been indexed by Google yet, I don't think.
It'll be on the Eventbrite though.
Sites.google.com/site.
That's the one.
Bingo. Google knows everything. They and NSA. Actually, this is a big discussion in Germany at the moment with NSA spying us. The funny thing was Merkel completely ignored the whole thing. This was not a political discussion at all. But as she figured out somebody spied her mobile, she's totally pissed off. It's really so funny. So don't mess up with this lady. If you go here, I have two setups. One is not really working too much, but this looks cooler at the moment. This is what I'm working on. Oh, come on. So that's a project I work on in Norway, if it comes. Come on. See, it works. Hello, Houston. Or this sucks.